Thank you. So I'm sure a lot of you have heard on the news that California has like a 30% chance of having an earthquake on the San Andreas in the next 20 years, and it's all doom and gloom. It's all going to be over, fall into the ocean. But that's not exactly true. They're really good at some things, like building things that survive earthquakes, and they've had a good record in the last 20 years. But what I'm going to talk about today is really how they get to this point. How do they know that it's a 20, 30% chance of having an earthquake? And I and Liz and a few other people like Rocco Malservisi and so forth from USC have been studying, USF, Freudian, I suppose, have been studying some of the faults in the Mojave Desert here, not the fun part of California, but certainly a good place to get crystal meth. But why do we care about earthquakes? And there are some really good reasons here. One, the top row here, from the Loma Prieta earthquake, infrastructure breaking down. You certainly didn't want to be on the Nimitz Freeway that way, or at least you didn't want to be going southbound. The Marina District in San Francisco. On the bottom half, Los Angeles, 1994, Northridge quake, 6.7 earthquake, happened in the middle of the night. Again, infrastructure. This is a special kind of earthquake damage here. This is self-inflicted. The morning after the earthquake, the guy in one of these buildings realized he smelled gas. There was a gas line break, and he wanted to move his car out of the way, which set off an explosion that burned down the neighborhood and killed himself. Brutal. But this kind of damage is certainly tragic, important, a key reason why we want to do it. But there's also a broader implication. I know a lot of us kind of think, well, that's the other side of the continent. I'm a long ways from earthquakes. Why do I care about this? Why should I pay for seismic hazard assessment in a place that's a long ways away? Well, California happens to be the 8th largest economy in the world if it was its own country, and that puts it somewhere between Italy and India, or France and somewhere else, depending on whose survey you do. But in reality, the reason you should care is because California produces more wine drinking by Americans and Floridians than any other place in the world. And this is a kind of tragedy we don't want to see. I'd rather see kids crying in a far off country than see a barrel empty like that. I'm just kidding. I'm not that awful of a person most of the time. Of course, California isn't the only place we have earthquakes. A lot of these are out in the west, like Alaska, Missouri, Hawaii, Nevada, Montana, Idaho. But we have big earthquakes here. In fact, a pretty sizable one happened in South Carolina you might not know about back in the 19th century that rang church bells in Boston. Camoli. I bet it didn't feel too good here either. A year after I got here, there was a 5.8 in the Gulf of Mexico, which was the first and last time I gave an interview to any kind of media before. Till tonight. So back to that map. How do we get the seismic hazard data that can let us know what's going on these faults and how dangerous are they? When's the next time they're going to slip? What are the odds on it happening in the next X number of years? Well, to build this map took thousands of different people, thousands of studies from folks in the USGS, lots of people doing individual studies for independent studies for places like hospitals and nuclear power plants, and then a lot of academia doing studies, including hundreds of students doing their own studies on these faults. And what they've had to come up with were essentially the answers to 4 different questions. How fast is the fault going? Which relates back to how often it has earthquakes. The faster the fault, the faster it gets to the next earthquake. When was the last earthquake? And what is the time interval between the earthquakes, also related to the speed? How fast is the earthquake? We can get at this a couple of different ways. One is through geodetic methods. We all have some kind of GPS in our cars nowadays, but you can use that for something other than finding a bar. You can actually use it to locate a place on the planet incredibly precisely if you have super expensive GPS. We're not talking TomTom here. We're talking $15,000 for a GPS. It seems exorbitant, and it is. But with that, you can get down to sub-millimeter, correct me if I'm wrong, Rocco, sub-millimeter locations of points on the planet, which is what you need to make a map like this. I'm going to come back to this map in a little bit, so if it looks confusing, that's because it probably is, even to me, but I'll try and explain it, and Rocco will roll his eyes. The other way we can get at it is geologically. We can go out and collect data from the actual Earth itself and determine how fast faults are slipping. There's Rocco now, sitting in front of a GPS meter. $15,000, friends. $15,000 right there. In Mexico, you have to put this thing in a very specific place. We call these things monuments. Revisit them every year, every couple of years. You can also set up GPS to record in a single place continuously. There are only a few of those, but there are a lot of these kind of temporary campaign stations that get revisited all over the planet. Not every year, but they get revisited a lot. These certain ones down in Baja were put in place back in the 90s, so they've seen a number of revisits, and we have a pretty good determination on those. The ones in the Mojave have been there maybe even a little longer, I'm not sure. But if you go out there and you visit these over and over and over again, you can determine how fast that one monument has moved relative to some place way far away that's supposedly stable, like, for example, Denver, Colorado, way away from the plate boundary. You can figure out how fast that station is moving on an annual basis. And that's what this map shows. It shows a bunch of stations located in the center of these circles, and the length of these lines relates to how fast that station is moving. That says 20 millimeters. This is going a little bit more than 20 millimeters. This is a map, by the way. of Southern California between Los Angeles in the south, just off the map, and Las Vegas in the north, just off the map, where there are a bunch of faults that carry some of the plate boundary strain. You guys know the San Andreas probably is the plate boundary fault, strike slip fault between North America and the Pacific plate. It turns out there's a whole host of other faults, like these guys out here, and a whole bunch in Los Angeles and Southern California on the other side of the San Andreas Fault, that also carry some of the slip. And they're every bit as dangerous, and some of them are even more dangerous than the San Andreas, because some of those faults are actually located in Los Angeles or located in downtown San Diego. And so we have to take those into account too. Well, we can use GPS in this case to actually estimate the rate of slip on this network of faults just to the northeast of the San Andreas. And Rocco and Liz and I worked on the Calico Fault, located here in the middle of the Mojave Desert, just to the east of Barstow, which is kind of like Marrakesh or Venice. It might be more the Venice of the Mojave Desert. Is that about right? Yeah. If guys and wife beaters are what signifies Venice, which I think it is, that is Barstow. Yeah. All right. So we did a study on this guy, a geologic rate assessment, which is the other way we can determine the rate. And in this track, what we actually do is we go out and look for landforms, features, geologic features, which are both offset by the fault and that we can date. Out here in the Mojave, there are a lot of open alluvial plains where flash floods have brought lots and lots of gravels and debris out. And then later on, younger flows have abandoned those surfaces. And in this case, they've cut a nice straight edge that was ultimately offset by the Calico Fault. The offset is about 85 to 90 meters, so that's maybe 300 feet, okay? Something like that. We also went out and dated a whole bunch of boulders on here. This is a little bit different dating. Sorry, Mary. Jesus, I don't know what was going through my brain there. This is a little bit different dating than what you may be familiar with, where you can date when a rock formed. This dating is how long has this rock been sitting out at the surface. It's kind of like the rocks get a sunburn, and how deep is that sunburn? And the longer it's been out there, the more of a certain radiogenic element, like beryllium, is collected in the rocks. And if you do some chemistry on it, you can actually figure out how much is in there and use that to determine how old the rock not is, but how long it's been sitting out on the surface. So we did that for a number of samples here, and we determined that this guy was sitting out here for something like 50,000 years, which means that this fault, slipping at a rate, an average rate of about 1.7 millimeters per year. or about a quarter of an inch. No, not quite. About an eighth of an inch per year. That's pretty slow, but the funny thing about faults is they can move fast, they can move slow. The earthquake in the end doesn't really care. What matters is how long is this fault. And this fault is over 100 kilometers long, and if the whole thing ruptures, we could be looking at a high 7 earthquake on this fault running past the Venice of the Mojave Desert, which no one wants. Well, that answers the slip rate question, but the questions about when was the last earthquake, what's the time interval between the earthquakes, and how big are the earthquakes that it has, for that we have to do a little different type of detective work. And these questions are usually answered by Paleo Seismology, which is kind of like paleontology. Paleo Seismology isn't on that? No. Oh, jeez. Seismology. Did I get it? I don't know that word. That is a foreign word to me. Maybe I'll get to that in a minute. But paleoseismology is essentially the study of earthquakes that happened before recorded history. And the way you get at these guys is most often by digging a trench. This is one in the Anzo-Borrega Desert. You can see it looks like a fun, exciting place. Not quite as good as Death Valley, because you had to walk all the way out to this trench, and it was 100 degrees on the day we walked out there, which was a cool day in the Anzo-Borrego. And Tom Rockwell's student dug this by hand in the middle of the night, which is the time you dig a trench in the Anzo-Borrego Desert. In case you need to get rid of something or someone, do it in the middle of the night, because it's blisteringly hot here. Anyhow, dig a trench across the fault. That's kind of critical. You want to get it across the fault. Once they have the trench dug across the fault, they grid it up. These are 1 meter squares on here. Photograph everything, and then they scrape it down very fine and map it out, getting every single layer and every fault that offsets that layer, and they pound a nail in there. Can't really see it because they put stars on there. They pound a nail in there for intersections of faults and layers that are offsets, and any place where they took a sample. And in this case, they generally do radiocarbon or carbon-14 age dating. I don't know if you saw it in the first picture of this trench. There's some brush in the back. Back in the day, a couple of thousand years ago, this was a much more humid place, and there was a lot more sagebrush around. But even if there wasn't, there's sagebrush in the hills, and there are occasional fires that burn that sagebrush, and that charcoal rolls down the hill in the floods and storms that comes, gets deposited in here. And that sagebrush carbon-14 age they get is the exact age or the exact time that plant died. It's a record of the time since that has died, so it's an incredibly accurate date, provided that charcoal hasn't been sitting around a while. The one problem in this place was that there happened to be a Native American site just uphill from it, and they did get some crazy scattered ages, which is to be expected because they were probably hanging on to wood for generations when they made something made out of wood or maybe made out of bone. That stuff sticks around. That's a particular problem in places like the Middle East where people have been hanging on to wood for a long time. I hear that's unhealthy. Okay. You've done the map. You've generated a map of the trench. Now comes the fun part. When you have the ages of each one of these layers, and then the determination of the offsets of those layers, you can actually determine when these earthquakes happen. For example, this fault offsets layer B, but it does not offset layer A. So you know that the fault had to have happened after layer B, so whatever age that is. But before the deposition of layer A, you have some bracket on its age. You know approximately when it has happened. Same thing with all the rest of these here. You can also use these offsets to determine how big the earthquake was. These things have vertical offsets. You can use those based on the recent earthquakes we've had in the last 100 years or so. Every time there's an earthquake, every nerd like me runs out the door with their laser rangefinder and their LiDAR equipment, and now they have drones. In the good old days, you had to climb inside an airplane. In Mexico, this is a lot of fun. There's a big crack in the floor of the airplane. You're trying to shoot your camera out of the crack to get a picture of the fault. Yeah, much easier now. You're on the ground like with a remote control. But every fault earthquake event they've had for the past 100 years or so, particularly the ones in North America, but increasingly around the world, has been studied to pieces for how big was the earthquake, what was the surface offset, how long was the surface offset, so that they can turn that into a magnitude when they dig a trench across the fault. Oh my God, it's the first time I said magnitude? Yes. Shouldn't it count if it was on a slide? I typed it out every time. There were like 10. All right. Oh yeah. Seriously? All right. Plate tectonics. Oh yeah. All right. I haven't said earthquake? All right. That's all I've been saying. All right. So the other thing from this trench, because there are lots of faults in here, and some of them you can see offset lower units and not upper units. There it's offsetting D and not C as opposed to B and not A. You can actually reconstruct the recurrence interval, or you can determine a recurrence interval, the time between each individual earthquake, which is another big function in determining what the seismic hazard of any individual fault is. The other part of this that I didn't really mention was that these faults are of different age. They have evolved differently. And so some of them, like the San Andreas, which has been around about 12 million years in some form or another, in its present configuration, it is a very old fault, and it's capable of rupturing long distances, but there are some complications for some of those smaller faults, like the ones out here in the Mojave Desert that we've been studying, because they have only a small amount of offset. San Andreas has 300 plus kilometers of total offset, whereas the ones out here maybe have 11 or 12 kilometers on the high end. That means they're relatively juvenile faults, and so they don't rupture long distances and generate huge earthquakes. But the San Andreas isn't fooling around. 1906, the rupture in San Francisco was a 7.9. That's near the top of the scale for a strike-slip fault. That's a pretty big earthquake. And it did a lot of damage. The people actually did more of the damage to themselves with the fires in San Francisco than the earthquake probably did. But a 7.9 today could have some rather catastrophic results. Before I leave this, I want to show a video. This is from the Southern California Earthquake Center, which is a consortium of the USGS and lots of universities studying faults in Southern California. And what this video is going to show you is an earthquake rupturing on the southern end of the San Andreas. Here's the city of Los Angeles. The fault is going to rupture up the San Andreas, and you're going to see the actual kind of seismic waves rolling through the region, and you'll see that Los Angeles gets special attention from the earthquake, particularly an earthquake coming from the south rupturing to the north like this. It's about 1 minute and 15 seconds long, but it's a 4-minute long video. And you can see the scale on the bottom here. This is the acceleration of the ground surface, or the velocity of the ground. It's not the acceleration, but you can see that things get rocking and a-rolling pretty quick. If there was sound for this, it would be screaming and glass breaking and people like, my drink! No one cares about Palm Springs. I'm sorry, Mary. Temecula's gone, Mary. Sorry. Los Angeles sits in a great big basin, which was great in the early 20th century because there's a lot of oil there. And it was a, car community. But it's not so great when the San Andreas, particularly when the San Andreas ruptures from the south to the north. It's a whole different story when it ruptures from the north to the south. It's not nearly as devastating. But from south to north, it's ball game because the shaking goes on here almost 3.5 minutes, and it's pretty intense. The other thing is the San Andreas is not the most dangerous fault in Los Angeles. In 1994, there was a blind thrust earthquake on a fault that was dipping underneath the Hollywood Hills, right under the Hollywood sign. And it was a 6.7 earthquake, and something like 43 or 49 people died. I can't remember the exact number, which is actually pretty incredible, but it was aided because it happened at like 5 o'clock in the morning. People weren't on the highways, they weren't in the buildings, they weren't in the parking garages. But that fault didn't have a surface rupture. It was a blind thrust fault that didn't actually go all the way to the surface. And that was the second one of those in 2 decades in Los Angeles. And they started to realize, holy cow, there's probably a bunch of these we don't know about. So they went to the oil industry, who had already drained the LA basin of all its oil, and they were more than willing to hand over their seismic profiles at that point. And they realized that right underneath downtown Los Angeles is this Puente Hills fault that literally projects into the tallest towers in downtown Los Angeles. And it is more than capable of producing a 7.5 earthquake, maybe more. there are 3 segments, and that is the estimated magnitude of just one segment went. And if you remember Tohoku in 2011, they predicted that essentially those faults didn't stitch more than 1 or 2 segments, and were shocked and surprised when it stitched 5 of them, and Fukushima ended up having its generators flooded and melt down. Well, fortunately, Los Angeles wasn't dim enough to build a nuclear reactor in downtown Los Angeles. But if it happens in the middle of the day, that could be some real trouble. Well, they had earthquakes before, but they were rare and considerably smaller. Okay, yeah. So the question was about fracking and how is that driving seismicity in places like Oklahoma. It's not actually the fracking itself that is causing it, because they're just pumping up the pressure in a small confined area to break up the rock to make higher porosity and permeability to extract the gas, oil that they want to get out of it. But what's the problem is that there's a lot of fluids that no one wants to have around that have to be dealt with some way. And so the way they get rid of them is to pump them down deep into the earth. And what that is doing is increasing the pore fluid pressure deep in the earth where there are faults that have some amount of elastic stress built up on them. The rubber band is stretched, in other words. And so it pushes them closer to failure. And the more they pump down there, the more they push these faults towards failure. And there is temporally and spatially a very strong correlation in this. So it's hard to argue that it's just a natural, this is just going to sort of happen, you know, because it doesn't happen where it's not being done, and where it is being done, it's happening. They're just now starting to admit that, and I think they're starting to not do it where they're seeing the earthquakes in Oklahoma. But the reality is this is a lesson we should have learned in the 70s from the Rocky Flats incident in Colorado. You pump lots of fluids at high pressure deep into the earth, you're gonna awaken beasts you don't want to do. Think, you know that scene in Lord of the Rings? Some kind of big fire demon? Something like that. Yeah. So in the Proterozoic, so in the Precambrian, before life really exploded on Earth, there was a continental rift that failed running through the middle of North America. So unlike on the East Coast when Pangea broke up and Africa and Europe went away, and South America, this didn't go to fruition. It didn't break apart. So it is a big tectonic scar in the middle of the continent, a fault just like the ones I was just talking about in Oklahoma. It is a fault that is present, that is capable of slipping, and because North America is actually being stressed from both sides, it's being pushed from the Atlantic side by spreading in the Atlantic. It's being pushed maybe or being pulled to the west by tectonics out to the west. Stress is able to build up on those faults, and so those faults, even though they don't have earthquakes very often, like I was saying, the fault doesn't care how long it takes to accrue the elastic strain to have an earthquake. It'll go until it reaches the breaking point, however long that takes, and when it does, however long that fault is, however big the surface area of the fault is, that dictates how big the earthquake's going to be. And that's exactly what's happened there. A really great place that exemplifies that is kind of the Armenia, Georgia, Azerbaijan, northeastern Turkey area, where supposedly there's only 1 millimeter of shortening a year going on there, and there are lots of faults. But in just the past 3,500 years, there have been 11 7+ earthquakes in that area, which is a great place to go study earthquakes because it's all in the churches. When a church falls down, they break up the tombstones in the graveyard to rebuild the church, which is like writing on the church when the earthquake happened, more or less. It's wicked cool. Not to mention, it's just a wicked cool place to work. Wicked. Wicked cool. Wicked's not on there? Matt was huffing glue on his way over here, and he asked, given the north to south rupture on the San Andreas, which is more likely to be an accurate depiction of the earthquake? The 2012 movie with John Cusack, or the Rock San Andreas movie? Well, The Rock at least involves, I think Dante's Peak. I'm going to go with Dante's Peak on this one. That seemed like the most likely to be an accurate movie. Neither one of those. Now, any day a lava flow flows uphill on Wilshire Boulevard is going to be a good day. I like how that hit most of the most expensive real estate in Los Angeles. That's the way to do a movie. Should have seen it roll through Bel Air. That would have really been. They transmit a long way, and the New Madrid is just one of a myriad of faults that, I mean, all those mountains up in the Appalachia, I mean, they were lifted up, jutted up rocks, lit up on faults. Deeper down, there were older, you know, normal faults that could be reactivated. Old faults are, you know, responsible for a lot of the seismicity away from plate boundaries. I grew up in New England. We had earthquakes up there every 5 or 10 years, and they were related to the fact that that part of the world was under ice 14 or 18,000 years ago, and so it was all pressed down. And then when the ice melted away, the land started to rise back up, and as it does, it kind of does it in piecemeal, and those old faults build up some stress, and then boom, they let go, and you have an earthquake. Not a big one, but certainly enough to wake people up in the middle of the night, as it did my mother, who grabbed me to pull me outside. Earthquake was 100 miles away. It was a 5.1, and I didn't wake up until someone was shaking me. But they're going to happen. And if you look at, if you Google, you know, historic earthquakes or the history of earthquakes, you know, maps of the world, you'll see that they're not all on the plate boundaries. There's a smattering of them away from the plate boundaries, particularly in places that have had seismic activity in the past billion years. It's not tectonic activity, not just seismic activity. Of course there. Sorry about that. It's Rocco's fault. We all know. We talk about it most of the day. All right, well, I should probably preface this by saying I was out there for the 1999 Hector mine earthquake, which ran through the military base out there. It was a 7.1, something like that. It was a pretty good-sized earthquake, and its epicenter was about 50 kilometers away from where I was, which was in the Clark Mountains, where I had been doing a class. I was a grad student at the time, and the class didn't actually start till the next morning, so I spent all night drinking heavily, and I was sleeping on a tarp next to my buddy, and some point in the middle of the night, I woke up and I thought, oh my God, I've got the bed spins. I was like, oh, it did not feel good. And then Jeff, my buddy, sits up next to me and I go, no way, he's got the bed spins too. This is something else. And I said, is this an earthquake? And then we were out with a bunch of seismologists. I'm not going to say it. And they started hooting and hollering before Greg Davis, the instructor, jumped up and said, that could be in Los Angeles. Don't get excited yet. So at that moment, we were all crapping our pants that our loved ones were in the middle of a big earthquake because we were 250 kilometers away from Los Angeles. And lo and behold, it was in the Mojave Desert. Now, to answer your question, I would say try and be in the Mojave Desert when it happens. But if you're not, you're not. Depending on the building you're in, if you're in a high rise, don't run outside. If you're on a higher floor, try and get to someplace in the triangle of life, like in a corner, under a table, whatever, away from floors potentially collapsing. You should have a certain area that might be protected in the corners, in a door jamb, maybe. If you're in your house, you certainly could run outside. There's little that's going to fall on you from your house unless you live with the Cardassians. But you're probably all right in your house because most houses are made out of wood and they're flexible and they will sway a little bit, and even if they do fall over, they aren't likely to collapse on you. If you live in Los Angeles and you live in one of these places that has a weak or a soft lower level, like the first place I lived in Los Angeles, we parked under the apartment complex, well, you're probably dead. Because those soft lower floors, remember that picture I showed you of the San Francisco earthquake there with the houses? That was a soft lower floor. Those usually collapse and the rest of the building collapses with it. And in the 94 earthquake, a lot of the people who died in apartment complexes where the soft lower floor collapsed. It's pretty, there's certain images of that are just not right. I don't know why I have seen them, actually. Don't live in an apartment complex with a soft lower floor. That's the method. I gotta go to bed.
Thanks to the reprobates that just nerded out with their science for you.